Hi everyone. In this lecture, we will discuss about single stage voltage amplifiers. So essentially MOS based single stage voltage amplifiers. So voltage amplifier is actually a 4-terminal device. So wherein you apply your input voltage between two terminals and the output voltage is taken across two terminals. Now there is a fixed relationship between the voltages between the four terminals, so which is V naught equals A times some gain times the input voltage. Okay, so every practical voltage amplifier has a finite input resistance and a finite gain. So I'll draw the model for a voltage amplifier. And a finite output resistance. Now, there are very simple reasons why such things exist: input and the output resistances. So, that can be very easily seen as. So, for example, if I connect any voltage source as an input to that with a finite source resistance, let's assume that the input Vs is an input that has to appear entirely across the input terminals of the amplifier. Then it can fully amplify it to a voltage and deliver it to a load resistance connected at the output. But in reality, there is always the gain. The gain that of an amplifier is also a function of the load resistance that you connect to the output terminals, and it is also a function of the source resistance that you connect to the input terminals. So how is it a function of all that? To relate that, Rin and Rout seem to be a very useful metric to do that. Also, you can see them as finite power loss elements. So the power that is delivered to the input of the system, if assuming source resistance is finite and Rn is also finite, is limited by the input resistance because there is some amount of loss at the input. And similarly, if we are delivering power to the load resistance, a fraction of that power will be lost in the amplifier itself. So that is what R0 and Rn capture. This is the other way of looking at it. But purely from a voltage gain point of view, we will see how Rn and R0 actually capture the loss in the gain of an amplifier. So when I connect a source resistance, a source signal with its own source resistance, and we already know we model source resistance to capture the finite power delivering nature of the source. Okay, and when you connect it to an input, I have actually written two terminals here and two terminals here. In most cases, the third terminal will be the common terminal, and it's normally a ground. Okay, so generally amplifier can be either 3 or 4 terminals. Generally it's a 4-terminal device, but since one of the terminal is common to both, generally it happens to be a 3-terminal device. Now in this, if I write the overall expression for the gain, so first I'll call this term as VOC, the open circuit gain, okay, open circuit voltage, and this voltage across the load resistance as V0. So if I want to find V0 by Vs, it's going to be Vin by Vs into VOC by Vin into V0 by VOC. Okay, so this term VOC by Vin, you can directly read it from this circuit. VOC is A0 into Vin, so VOC by Vin is equal to A0. This is called the intrinsic gain. So this is the maximum gain that this amplifier can give you. Okay, with the maximum gain this amplifier can give you. Under what conditions we will see now. And Vin by Vs is the input voltage delivered to the amplifier, which is Rn by Rs plus Rn, and this will always be less than 1, which means the entire voltage, the input voltage, which is Vs, will not be fully delivered to the amplifier. A part of it, only a fraction of it, is only delivered to the input. And similarly, V0 by VOC is RL by RL plus R0. So again, this is also always less than or equal to 1. This will be equal to 1 when RL tends to infinity or R0 tends to 0. Again, this term will be equal to 1 when Rin tends to infinity or Rs tends to 0. So the overall gain of the amplifier, I am going to take modulus here so that to just take the sign as positive, will always be less than, A is always less than or equal to A0. A0 is the intrinsic gain of the amplifier. So intrinsic gain, you can see that as when Rn is infinity and RL is infinity, you get the intrinsic gain. Okay, even if you have finite Rns and R0, you will still get a finite, the gain to be the intrinsic gain. Or you can also have an RS is 0 and R naught, RS is 0 and RL is infinity. Either of these conditions will give you, the maximum gain from this amplifier. So A naught here is the maximum gain that you can get out of an voltage amplifier. Okay, and R in and R out actually reduces the overall gain. Reduces the gain of an amplifier from the maximum gain by some value. Okay, so that's why we are very much interested when given any amplifier architecture, you will be trying to find out the R in, the input resistance, the intrinsic gain, and the output resistance. Okay, so we'll take in MOS circuits, we are going to use a MOSFET as an amplifier. A MOSFET has 3 terminals, so it has gate, drain, and source. Since it has 3 terminals, and I actually need to form a 3-terminal amplifier using this. Okay, so if I need to form a 3-terminal device, 3-terminal amplification possibility, so meaning amplifier I said is a 3-terminal device. If I assume one terminal to be common terminal, then if I can apply input in one terminal and take output at the other terminal, and the third terminal becomes the common terminal, and all the 3 have to be unique, they can't be the same. Okay, so by that I can simply say that there are 6 possibilities, 6 possible configurations, out of which I have to eliminate the cases where, because I can't give input at the drain. Okay, I have to eliminate the possibilities where I can't give the input at the drain, and similarly I can't take output at the gate. If I eliminate that, I'll be left with only 3 possibilities. So the 3 possibilities are common gate, common drain, and common source. Okay, now one of the most popularly used one is the common source configuration. So how do you call it a common source or common gate? Is that you first see where the input is applied, and then see the output terminal where the output is taken. The third terminal becomes your common terminal. So for example, in this case, your input is at the gate, output is at the drain, and therefore the third terminal becomes the common terminal. This is the common source configuration. In a common source configuration, we are interested in finding what happens when I load this amplifier with a source, a finite source resistance, and a load resistance. Now the input resistance of a common source configuration, you are looking into the gate, therefore it's infinity, and so the entire input voltage Vs appears across the gate to source terminal. Okay, but the output resistance is actually R naught. To find R naught, you just have to output resistance, you have to just short circuit the input and measure the output resistance seen at the output terminal to ground or to the common terminal. So in this case it will be small R naught. Okay, that will be 1 by lambda into I, the quiescent drain current. Now first we will try to find the intrinsic gain. That will happen when RL is infinity. So when you make RL as infinity, the intrinsic gain of this amplifier will be minus GM into R naught. So this is the maximum gain you can get get using a common source amplifier. If you have RL in presence, RL in the presence of RL, the gain will be, so you have a current GM. Now that's going to flow through resistance RL parallel R naught. So the gain is going to be minus GM into R naught parallel RL. So this can also be written as minus GM R naught into RL by RL plus R naught. So now if you look at it, this term is always less than or equal to 1. So therefore your gain will always be less than minus GM R naught. So I am going to call A naught as the intrinsic gain, which is minus into GM into R naught. So the maximum gain for a common source configuration is minus A naught. With the sign itself, if I take magnitude, it will be just A naught itself. That happens when RL is infinity. And the output resistance of a common source configuration is small R naught. Here source is at ground, so then you get small R naught, and the input resistance is infinity. These are all low frequency parameters. Okay, it's infinity for the common source amplifier. Now the next amplifier we'll be analyzing is a common drain amplifier, also called as a source follower. A common drain amplifier is one where the input is at the gate and the output is at the source. The third terminal, which is drain, becomes the common terminal. First, we will analyze what happens when R0 is infinity. Okay, if R0 is infinity, then there is no path for the current. So your GM into VGS is 0. Okay, there is no path for the current. So therefore, and here I have assumed R0 is infinity and RL is also infinity. It's the open circuit gain which you are trying to find. Your VG will be equal to Vs, which means the source voltage will follow the gate voltage. So therefore, it's called as the source follower. Okay, so your V0 will be equal to Vi. It will transfer the voltage exactly from the input to the output. So then why do we use this as an amplifier? Why do we use the word amplifier for this? So you should remember, for any amplifier is a two-terminal device, VS-IS, the product of the input voltage source into the current drawn from it, is the input power. That is input power delivered by the voltage source. Now, by the input source, PL is V0 into I0, the product of the voltage into current across the load resistance. Okay. Now, PL by PS always has to be greater than 1 for an amplifier. Okay. You can actually see a circuit like a transformer with 1:n turns. There will be a voltage gain in the circuit. If you apply voltage V1 for ideal transformer, the voltage across the second terminal will be n times V2. But you should also remember that the current is getting scaled. The second terminal, the current will get scaled by a factor n. So I2 will be, so this is n times V1. Yeah. I2 will be I1 by n. So that the product V1 I1 will always be equal to V2 I2. In fact, if you consider losses, then V2 I2 will always be less than or equal to V1 I1. So therefore, you cannot call a transformer as an amplifier, voltage amplifier. Okay, you cannot use it in the first place, and you cannot call it as well. But a common drain configuration, the maximum gain is 1, voltage gain. But if you look at the current gain, a common drain configuration will be able to deliver some current to the load resistance, okay, by drawing no current from the input. So therefore, the input power drawn is actually 0. But there will be a finite load power which is delivered to the load. Okay. So therefore, the ratio will be infinity. Actually, it has an infinite power gain. Therefore, in that definition, we will call it as an amplifier. And similarly, for a common source configuration, though we haven't discussed it now, again the input current drawn is 0 at low frequencies, and the output current is finite. So therefore, the current gain is infinity. AI, I am going to call it as a current gain, which will be infinity. The power gain, which is PL by PS, is actually AI into AV, the voltage gain into the current gain, which again is infinity for a common source configuration. In fact, if I assume R0 as infinity, the gain of a common source configuration will also be infinity. So it is minus GM into R0, which will tend to infinity if your R0 is infinity. But for any finite R0, you get a maximum gain of GM into R0. So now, once we know how to analyze a common drain configuration, I mean open circuit, now we will try to include the non-idealities, which is finite R0. If I have a finite R0, I can simply draw it, because R0, the other terminal is at AC ground. We have applied input, and so output is across R0. So now if you see, the input is getting divided, a fraction of the input is appearing across the gate to source voltage, and a fraction of the input is appearing as output. So your Vi is VGS plus V0, or VGS is Vi minus V0. You can actually see that this circuit is actually like a feedback system. Okay, Vi as an input to the system, Vi minus V0 is the error. Okay, that times GM is the current that is generated, which then flows through R0 and creates the voltage drop V0, and the feedback is closed. So this product R0, I am going to call it as A0, which is GM into R0 is A0. So I will call it as A0 like this. Okay. So this system, the open loop gain is A0, and the closed loop gain of the system is A0 by 1 plus A0. So a common drain configuration can be seen as a feedback system with this. Now this is always going to be less than or equal to 1. If A0 equals infinity, then this will be equal to 1. Otherwise, it will always be less than 1. So this is the maximum or the intrinsic gain of a common drain configuration without any loading effects. Now if I load the circuit, then the gain is going to change. So how do we find the gain in that case? So I am going to connect a finite load resistance, and you are supposed to find the gain of this circuit. Now to find the gain, what I'll do is I'll just find the Thevenin equivalent as seen by the load resistance, and then the circuit becomes much simpler. So first I'll have to find the open circuit voltage gain, which will be A0 by 1 plus A0 into Vi, and the output resistance. Now to find the output resistance, you have to short circuit the input. Even if the input has source resistance, it doesn't matter because the input current drawn is 0. Now you are looking at this terminal, it will be 1 by Gm parallel R0, so I'll approximate it to 1 by Gm. That will now be connected to RL. Okay, so if you look at this is actually 1 by Gm parallel R0, which can be written as R0 by 1 plus Gm R0. This can also be written as R0 by 1 plus A0. Okay, but if you assume Gm R0 much greater than 1, you can approximate it to 1 by Gm. So your overall gain is going to be A0 by 1 plus A0 into RL by 1 by Gm plus RL. Okay, so now if you look at it, the output resistance has reduced for is actually much lower, which is 1 by Gm for a common drain amplifier, whereas for a common source amplifier the output resistance was R0, which is very high. Okay, so this common drain amplifier actually behaves like a true voltage amplifier because your output resistance should be as low as possible for a voltage amplifier. Okay, and using a single MOSFET, the lowest resistance you can get out of that MOSFET using a single MOSFET is 1 by Gm. Okay, so this is going to be A0 by 1 plus A0 into Gm RL by 1 plus Gm RL. If your Gm is very large, then yes, the gain is going to be approximately equal to A0 by 1 plus A0. Okay, so for a common drain configuration, to summarize, the intrinsic gain is A0 by 1 plus A0, where A0 is Gm R0. The output resistance is 1 by Gm approximately. It's actually 1 by Gm parallel R0, but I'm approximating to 1 by Gm. And the input resistance is infinity. This is your output resistance, and input resistance is infinity. Now we will move over to the common gate configuration. In a common gate configuration, input is applied at the source and output is taken across the drain, and the third terminal, this gate terminal, becomes the common terminal. So I am going to apply a voltage source with a finite source resistance and then connect it to a load resistance. Okay. Now in a common gate configuration, so first we'll analyze the intrinsic gain. It's easier to analyze that. The maximum gain. So this is the circuit for a common gate configuration. So I'm going to apply a voltage Vi here. So if you look at this, Vi is actually minus VGS. So therefore, Gm VGS is the current that's flowing from drain to source in a MOS model. I can write it as minus Gm Vi flowing from drain to source, or a current Gm Vi flowing from source to drain. So I can just reduce it little. I'll redraw the circuit. So I can draw that as a current Gm into Vi flowing from source to drain. Now this current, as it enters here, this is an open circuit, so the current is 0 here. So all that current will loop back here, and it will create a drop of Gm R0 into Vi across R0. So now if you are asked to find the voltage V0, that will be simply, if you go around this loop, you will simply get V0, this is Vi here, I'm sorry. V0 is going to be 1 plus Gm R0 into Vi. So the maximum gain of a common gate amplifier, I'll write it as A max Cg, is going to be 1 plus A0. Okay. Now the next step is to find the input resistance and output resistance. Now in common gate and common drain common source and common drain configurations, we found that the input resistance was infinity. And we also found that output resistance was R0 for common source and 1 by Gm for common drain, low frequency output impedances. If you look at this, they both are independent of what you connect, whether you, what is the value of RS and RL you connect to the amplifier. Okay, but for a common gate configuration, you will see that the output resistance and input resistance will depend upon what you connect between source and drain. Now I'll just give a small example. Why does it depend upon that? So for example, let's say we want to find the input resistance of a common gate configuration, and then I have open circuited the drain. If I open circuit the drain, you will have a current GMVI flowing in this direction. Now that current, since this current has to be 0, it's an open circuit, it will loop back, and the GMVI current will be looping within the device itself. I mean, it will flow through the device and R0. The current that is actually drawn at the input is also 0. Okay, so because of that, it will look like an open circuit. You are applying a finite voltage, but the current drawn is actually 0. So therefore, your Rn is infinity if I open circuit the drain. Now I will short circuit the drain. If I short circuit the drain, what happens is that there is a current GMVI flowing, and this current, as it comes out here, this is like a short circuit, so all the current will flow through this path itself. So they will have the current GMVI flowing here. Also, there is a current through R0, because R0, the voltage VI will entirely appear across R0 because this terminal is at 0 volts. So you will actually have a current of VI plus R0. So 1 by GM will appear in parallel with R0. Currents are adding up, so they both are in parallel. So you can treat it as 1 by GM parallel R0. So your Rn will be approximately equal to 1 by GM. So now if you see, the value of Rn changes from 1 by GM to infinity as you vary your RL from 0 to infinity. Okay, so it's a strong function of the load resistance. Similarly, if you are asked to find the output resistance with your finite source resistance, and you are looking at this terminal, this is like a cascade amplifier with us, or you can see that as a degenerated common source. Now we are looking into the drain. The resistance Rs gets multiplied by GM R0, so approximately your Rout will be GM R0 into Rs. And also I haven't shown for Rin for a general RL. You can approximately show this to be 1 by GM plus RL by GM R0 approximately. Again, these are all approximate results. Okay, you can approximate them to 1 by GM plus RL by R0 or RL by GM R0. This will be you can show this result very easily. The input resistance of a common source configuration also depends upon the load resistance, and the output resistance of a common gate configuration or out also depends upon the input resistance or the source resistance. So that's all about single stage amplifiers. So we have discussed common source. The intrinsic gain was minus A0. So I'll write A intrinsic, R0 and R out. So your for a common source configuration, your R0 is going to be small R0. Sorry, this is Rin, and I'll write it as R0. So Rn is going to be infinity and R0 is going to be small R0. And for common drain configuration, the intrinsic gain is A0 by 1 plus A0, the max gain, and Rn is infinity, R out is approximately 1 by GM. And for common gate configuration, the intrinsic gain is 1 plus A0. The input resistance, again it depends upon the load resistance, so approximately we said is 1 by GM plus RL by GM R0, and the output resistance is actually GM R0 into RS. Okay, so this is for all the three stages. Now if you look at common source configuration, there is a 180-degree phase shift between input and the output, but in common drain and common gate configuration, both the input and output will be in phase for low frequencies. So this is all about single stage MOSFET amplifiers. Okay, so I'll stop now.